It is Ryan Seacrest here. There was a recent social media trend which consisted of flying on a plane with no music, no movies, no entertainment. But a better trend would be going to ChumbaCasino.com. It's like having a mini social casino in your pocket. Chumba Casino has over 100 online casino-style games, all absolutely free. It's the most fun you can have online and on a plane. So grab your free welcome bonus now at ChumbaCasino.com. Sponsored by Chumba Casino. No purchase necessary. VGW Group. Void where prohibited by law. 18 plus terms and conditions apply.
Hi there. Welcome to the Logic of Risk, episode 6. Today, we continue talking about frequentism, going into some more detail. Are you ready? Let's get started. In the previous episode, we said that, for frequentists, the probability of an event corresponds to its relative frequency over time, or, more precisely, to the theoretical value of that relative frequency. The idea is quite simple. When analyzing a random phenomenon, we record and study its occurrences over time, and we define probability as the ratio between the number of times the event of interest happens and the total number of outcomes we observe for that random phenomenon over time. Let's go back to the dice example and suppose we are interested in the probability of rolling a 5. If you have pen and paper handy, you might find it helpful to jot down what I will say. But don't worry, I will try to keep it clear even if you are just listening. Imagine rolling a die once. We observe a 3, no 5. So, with just one roll, the relative frequency of rolling a 5 is 0, meaning 0 fives observed, out of one roll. Result 0. Now I roll the die a second time and observe a 2. The relative frequency of rolling a 5 is still 0 out of 2. Again 0. I continue rolling the die and get, in order, 6, 6, 1, 4. After 6 rolls total, I've still observed 0 fives. Then, on the 7th roll, I get a 5, so I now have 1 5 out of 7 rolls, and the relative frequency updates from 0 to 1 over 7, about 14%. On the 8th roll, I get another 5. Now it's 2 fives out of 8 rolls, which is 2 over 8, or 25%. Then I roll a 3, so the frequency of 5s becomes 2 over 9, roughly 22%. If I imagine rolling the die many more times, say n times with n large, the relative frequency of 5s will tend to converge toward the limiting value 1 over 6, or about 17%. We call it a limiting value because theoretically you never actually reach it. It's a theoretical value that appears in the frequentist view when the number of rolls goes to infinity. In reality, we don't need to wait for an infinite number of rolls to see probability emerge as a relative frequency. Bernoulli's law of large numbers tells us that in a sequence of independent trials, like our dice rolls, as the number of trials grows, the relative frequency of a certain event converges to that event's probability with an error that becomes smaller and smaller. So, if we are satisfied with, say, a 3 decimal place approximation, we clearly don't need infinite time, something I personally don't have, and I doubt you do either. Notice that by saying that the frequency converges to the event's probability, we are affirming that such a probability exists objectively. Indeed, frequentists believe, and it's somewhat amusing to use the verb believe here, in the objectivity of probability. In the dice example, just a few dozen rolls are already enough to get probability values that are very close to that 1 over 6 which we know is the probability of rolling a 5 with a fair die. You might say, Why go to all this trouble just to arrive at the same result the classical definition gave us in 2 lines? Well, the point is that in the frequentist definition we haven't assumed equal likelihood, nor have we needed to count all possible outcomes. We only counted how many times a 5 came up out of n rolls with n large. At this point, it may be helpful to restate it clearly. For a frequentist, the probability of an event is the theoretical limiting value that its relative frequency tends toward if we repeat our random experiment an arbitrarily large number of times. So, if I'm interested in estimating the probability that a certain portfolio will lose more than 10,000 euros in a single day, all I need to do is to observe that portfolio or similar portfolios over time and note how many times such a loss actually occurs. Notice that, by the classical definition, such an event would be practically untractable, because I wouldn't know how to precisely describe the sample space, in which I should be able to count a finite number of equally likely outcomes. It's natural to ask what pitfalls might lurk behind the frequentist definition, and there are several. First, we are not always able to repeat and observe a given phenomenon a large number of times. It's not just a question of time and money. Should repeating the experiment and collecting data be costly? Personally, I would not set out to estimate the probability of a nuclear reactor meltdown using a frequentist approach, and not merely for monetary reasons. There is something deeper. Recall the distinction between mass random phenomena and single events. For a mass random phenomenon, we might hope to collect enough data to study how its relative frequency behaves, but we can forget about that for single events. Von Mises was aware of this, which is why his analysis primarily deals with what he calls a collective in English. A collective, he says, and I quote, is a sequence or collection of uniform events or processes that differ in some observable attributes, such as color, number, and so on. An example is all the molecules in a certain volume of gas, where the attribute might be each molecule's velocity, or all the wheat stalks grown by a certain farmer, where our interest lies in whether they have or not a certain parasite. For von Mises and for frequentists generally, the probability of interest is the probability of observing a certain attribute in that collective. Von Mises himself goes so far as to say that for single events it's impossible to properly define an objective probability. I can estimate the probability that a group of 40 years old Frenchmen will die before turning 41, but not for one particular individual, say Jérôme from Paris. This relates to the reference class problem, which we will look at more closely in the next episodes. This clear limitation to mass random phenomena is one of the main criticisms by Bruno De Finetti, along with more technical points like the Regellosigkeit axiom, the axiom of irregularity. We will get into those when we discuss the subjectivist definition of probability. To be clear, De Finetti always considered von Mises' work extremely important, appreciating and sharing many of its elements, like the critique of the classical definition's assumption of equiprobability. He also agreed that once probability is defined based on certain fundamental principles and minimal requirements, such as those we covered in episode 3 and which we will revisit soon, the mathematics of probability must be the same universally. True scientists may have differences in perspective, but they always maintain a deep mutual respect. Scientific dialogue thrives on diversity of viewpoints and is enriched by a free exchange of ideas, provided, of course, there is no room for absurdities, conspiracies, or anything like that. I would like to close this episode with some practical considerations on the frequentist definition of probability. In risk management, after all, we are interested in using probability to quantify the chance of damage, and thus, ultimately, risk. As mentioned, the frequentist approach is really only workable when you are dealing with mass random phenomena, those you can observe repeatedly over time to collect enough outcomes. Put simply, you need a lot of data you trust. And remember, by the way, that trust is subjective if you want to estimate a probability accurately. This automatically excludes one-shot events, which are very significant in risk management, but by definition offer no historical data for analysis. And while we might try analogy, looking at similar events observed elsewhere, that doesn't really help if the event you are considering is unique or nearly unique. Even in cases where the phenomenon is a collective, thus in line with von Mises' frequentist perspective, practical problems can still arise. Even if the event whose probability we want is a rare event, theoretically we might be able to gather enough observations over a long period, but in practice these might not be realistic. David Friedman, a statistics professor at Berkeley, pointed out that the frequentist method can't be used to estimate the probability that an earthquake with a magnitude above 6.7 on the Richter scale will occur in the San Francisco Bay Area before 2030. Even though earthquakes of that magnitude happen several times a year worldwide, you are not going to get enough occurrences specific to that region. And if you are interested in an earthquake above 8.5, thankfully those happen only every 20 or 30 years worldwide, so it's basically pointless to rely on a relative frequency. The weakness of the frequentist method is particularly obvious for random phenomena marked by high variability and extreme events. When we discuss heavy tails, sub-exponential tails, and fat tails, which are not at all the same thing despite common misconceptions, we will see that even substantial data can tell us little or nothing about very rare and extreme events, especially if we focus on just calculating relative frequencies. We do need more robust tools. Phenomena characterized by heavy tails, long tails, sub-exponential tails, and fat tails include wealth, income, telecommunication networks, financial portfolios, pandemics, wars and terrorist attacks when we assess the number of casualties, floods, storms, earthquakes, solar flares, and a thousand other things that are not exactly minor concerns in risk management. Moreover, unless we are dealing with very regular phenomena, say the thin-tailed ones, where extremely large or extremely small outcomes are negligible, the frequentist approach is easily victim of historical bias. This bias manifests itself when we assume the past is an optimal predictor of the future, and thus believe that enough historical data can accurately give us the probability we are interested in. For thin-tailed phenomena, many medical or physical measurements, for example, this is often true. If I gather enough data on people's weights, I can estimate quite accurately the probability of someone being obese, anorexic, or of normal weight. But believing the same holds for fat-tailed phenomena is one of the most serious mistakes in risk management. If I run a nuclear power plant and I have not seen a major incident in the last 15 years, assuming one cannot happen in the future is, shall we say, foolish? Once again, think of the Lehman Brothers collapse, which many geniuses assumed was practically impossible because it had never happened before, giving it a relative frequency of zero, just like the zero frequency of fives in our first few dice rolls. In risk management, there is a simple saying that seldom fails. If it has happened, it can happen again. If it has never happened, it can still happen. And the quote I would like to leave you with comes from John Maynard Keynes, whom we will soon discuss. It has been already pointed out that no knowledge of probabilities can help us to know which conclusions are true, and that there is no direct relation between the truth of a proposition and its probability. Probability begins and ends with probability. Talk to you soon. Probably. Ciao, ciao.
How to have fun, anytime, anywhere. Step 1. Go to ChumbaCasino.com.
ChumbaCasino.com. Got it.
Step 2. Collect your welcome bonus.
Come to Papa welcome bonus.
Step 3. Play hundreds of casino-style games for free.
That's a lot of games. All for free?
Step 4. Unleash your excitement.
Woohoo!
Chumba Casino has been delivering thrills for over a decade. So claim your free welcome bonus now and live the Chumba life. Visit ChumbaCasino.com. VGW Group. No purchase necessary. Void where prohibited by law. See terms and conditions. 18+.